Okay, so for today, we're finally in a position to go over the probably the most commonly used pulse sequence in the scanner of all, which is EPI, which is echo planar imaging. So the plan is to sort of go over how that works, and then probably the second most used, or actually now probably the most used sequence over single-shot EPI is multiband EPI. But to understand that one, we have to understand undersampling first. So second half we'll go over why can you undersample? So why can you undersample K-space? And then on Friday I'll talk about how multiband works. Multiband EPI. Multiband EPI is probably the most it's probably the most common sequence used in functional MRI. So the the idea of EPI is actually quite old. So it really goes back almost to the beginning of MRI, like in the 80s. People already were trying to figure out how to do this in the 80s. That's like 10 years after. It's only 10 years after the first back of the envelope calculation on how you might use MRI for imaging. So what is it? It's often called single shot. Single shot. And what does that mean? That just means one RF pulse. So a shot is an RF pulse. So basically the idea, if we go back to the very beginning of the class, if you do an RF pulse, so here's here's an RF pulse. What kind of transverse magnetization you get? Well, basically you just get an FID. So you get this FID, which looks like that. And it doesn't take very long. So, this might be, say, like 50 milliseconds. So it's a very short, that's just what happens if you do an RF pulse and you get free induction decay. So that's perfectly good signal. And so people have thought about, well, why don't we just try to collect all our data in K-space for a slice in the space of just this FID. So the idea is that you would turn on some gradient echo and generate a whole series of echoes like this, just in the space of the FID. So when we were talking about spin echo, we might do this, wait a while, do a 180, and then get an echo out here, much further down the line. But here we're talking about, let's just cram it all into that initial FID. And so that's the idea. Like I said, I mean, it's a very sensible idea. You just did a nice RF pulse and you got a signal. Why not just use it as quickly as you can? So what stopped people from doing that? Well, the main problem is you have to change the gradients very rapidly, because if that's 50 milliseconds and you want to collect all the lines of K-space, you're going to have to change the gradients maybe like 1,000 times a second. So you'll have to change the gradient in the space of 1 millisecond. And it turns out that when you try to change the gradients, basically when you try to change the magnetic field, and you've got some metal in there, and there's a lot of metal in there. The magnet is all made out of metal. The can that holds the glass that holds the liquid helium is all made out of metal. The magnet weighs 12 tons, so there's a lot of metal in it. So when you have that much metal around, and there's metal in the gradient coils and metal in the RF coils, when you have all that much metal around, if you try to rapidly change the magnetic field, you get what are called eddy currents. They're kind of currents that flow around in the metal when you move the magnetic field. And the effect of the eddy currents is to try to stop you from moving the magnetic field. So they act like taffy, like you try to do something and then they kind of push back. And so in order to overcome that, you need even more current. And so the reason they couldn't do EPI in the early days is their amplifiers weren't powerful enough. And I always like to, brag about the amplifiers. So now we have 3 1.5 million watt amplifiers. They're kind of like a stereo, a 3-channel stereo with 1.5 million watts per channel. And so the amplifier can put out 1,000 volts at 1,000 amps. That's 1 million watts. And so you need this very large amount of current going through the gradient coils in order to change them very rapidly and then overcome the eddy currents. So that's the main reason that people couldn't do this. And in the early days, they used amplifiers. They used amplifiers that were kind of like a stereo amplifier, and that doesn't make as efficient use of the transistors. And so what's done now is if you want, a gradient waveform that looks like this, if you blow that up, so if you really sort of blow up, what's going on in a little tiny piece of that gradient waveform, what's going on is the amplifier is just switching on and switching off like this. So it's actually a switching amplifier. It just uses the transistors as switches and just turns them on and turns them off. And it basically approximates the gradient waveform as a bunch of switches, very powerful switches, because the transistors can switch a lot of current that way. And by doing it this way, they were able to generate these amplifiers that are much more powerful, that will allow you to do EPI. So how does it work? So we'll look at the actual pulse sequence, and then look at where we are in K-space. So the first thing we start off with is the RF pulse. So here's the RF, and so we might do a 90-degree pulse, but as time has gone on, people have, they've been doing multi-band, which allows you to collect more slices more rapidly, and so they've had to actually, or say 50 degrees if TR equals 1 second. So now we can collect images at the rate of a whole volume in 1 second. So if we collect a whole volume in 1 second, then the time to the next 90-degree pulse will only be 1 second, and there won't be as much longitudinal recovery. And so it turns out there's a simple calculation you can do to try to figure out what is the optimal flip angle to give you the biggest signal. And remember that equation that sort of looks like this. So what is that number? What is this is flip. So for a given T1 and T2, what is the flip angle? You can solve this equation to find the flip angle that gives you the largest signal in the steady state. That's called the Ernst angle. So this is, if you want to look it up, Ernst angle. This angle right there. And so if you do that calculation, what you see is that using that gradient echo that we did the homework on, the first homework on, if you just do that calculation, you'll find that the biggest signal will be about 50 degrees if you're at TR1. And if you do TR1 90 degrees, you'll actually get less signal in the steady state. So that's the RF. And the first thing I'll do is erase that because I forgot to put in a critical part, which is the fat saturation. So here's the fat saturation. So remember what that is. That's to try to cause the protons in the fat, which have a slightly different resonant frequency, and so therefore will actually appear in a different part of the image. They'll actually be displaced. So this is a chemical shift problem. So what we want to do is like get rid of those guys. And how do we get rid of them? We saturate them, meaning we do a 90-degree flip at the frequency that they like, because remember the frequency that they like will be slightly different than the frequency of water because of the chemical shift. And so we saturate them, meaning do a 90 on them, and so then there's no longitudinal magnetization left. So that's the very first thing we do. And now there's a problem, which is that there's going to be some signal generated by that. And so one of the things that we can do is to try to get rid of that signal by spoiling it. GX. So we could do this on one or more gradients, but let's just sort of do it. We'll just do it right here. So this is a fat sat spoil. Because what happens is that fat saturation is going to generate an FID. And so we've got to get rid of it. We don't want to record that. So let's fat sat spoil. So this is always done. You can turn it off. If you turn it off, you'll just get there's a little layer of fat under your skin on top of your skull, and that you'll see a little white stripe displaced into the brain or sticking out of the brain on the other side. And that's because the resonant frequency of the fat protons is slightly different. So that's always done. So now we're ready to actually do our 90 that is at the right resonant frequency for, we'll just say it's a 90 or 50. TR equals 1. Put that back up. Okay, so now we do our 90. And since this is a 2D echoplanar imaging, it's a 2D imaging technique. We'll explain how you can extend this to 3D, but this is typically done as a 2D. We have to do a slice select. So here's the slice select, and here's the slice select fixer. So let's draw over here where we are in K-space. So here's our K-space. So the first thing we do is we'll ignore the fat sat, and then we do this 90 here, and so we can sort of imagine that the RF pulse, even though it's extended in time, started right there, and so we were in the middle of K-space there. And we sort of got everybody in line, but there's a gradient on, and so we're actually coming out of the plane in the z direction, because this is the K x direction, and this is the ky direction. But there's actually three-dimensional k-space, and so when we turn on that slice select in the z-axis, it actually moves this out of the board. And then we sort of fix it by getting back into the board, cancel that out, and so now we're at point A. So here's point A. So that's point A right there. So we go to the middle of k-space after we fix it. And the next plan is this is often done at the same time as we're fixing this, but just for conceptual clarity, we can sort of separate this out. Now we go to the far left side of k-space. So here's the far left side of k-space. So we turn on both the x and the y gradients at the same time. And so what does that do? So that puts us at point B. So if we turn them on both at the same time, what's going to happen is we're going to go down to the corner of k-space like that. So that will put us at point B. So when we were thinking about this whole sequence, remember, since we're not spoiling anything, it's kind of like we essentially, whenever you turn a gradient on, it moves you someplace in k-space, and then you pretty much stay there until another gradient comes on. So we go down here. We haven't collected any data yet, and then we turn the gradient on in the opposite direction. So here's the gradient on in the opposite direction, and then we keep it on for twice as long as it took to get to the bottom corner of k-space, because that was only half of k-space. So if we leave it on twice as long, then what's going to happen is we'll end up at point C. Now, let's put point B, point C over here. So that's where the echo occurs, the gradient echo. And then here's point D. So the gradient, so we messed up the phase here, and then we fixed up the phase here, same area there, and so then we get a gradient echo there. It's not a very big one because we're way out on the edge of k-space. So that echo is occurring at C, and so what is that over here? So we turn the gradient on, and half of that lobe got us to here, so this is where C is, and then the second half got us to here. So here's, so basically this is point C where the echo occurs, and then this is point D when we get to the opposite side of k-space. And so now we actually record data. So here we record a line of data. So if we're, say, doing 64 by 64 EPI, then we would record 64 data points. So that's one more line down here. That's the recording. So here's where we have the recording turned on. So here's our recording. This is A to D. This is the RF signal. So now what do we do? Now we turn on, the technical word is a blip. So if we go right to that point where we're crossing into the negative, we put a little blip on. So you just turn the gradient on for just about as small as you can. So what are these? What are these directions? This is slice select, because there's a 2D scan. And then And this one is phase encode. So these are the phase encode blips. Blip, that's the technical term for it, blip. It's just, if you just turn the blips on, it just sounds like little blips, doesn't make much noise. And then this is the readout. Frequency encode. Put it in quotes. Frequency encode. Okay, so now we're at the right side of K-space. And so, so what does the blip do? So the blip is typically turned on right while this other one is going, but let's imagine that we went down here and then just turned on the blip. So what will happen is that will basically just cause us to sort of go around the corner like that. And so what is that doing? Well, it's just moving us up. It's moving us up in K-space. It's unwrapping some of the spin phase that this initial going to the corner of K-space caused. So, but just a little bit of it. So, you know, it's a small blip. So we just undo a tiny bit of this. So it's kind of like, you know, it's kind of like the phase encoding where you repeat the experiment a whole bunch of times with a bunch of different levels of phase encode, except now what we're doing is we're just doing tiny little blips and continuing to record data from one 90, from a single 90. So now what we do, so that's the blip. So then we'll put E over here. So this is just after the blip. So here's E. Now we're at E. Then we just turn the gradient on the opposite way, and halfway through we get another echo. So here's another echo down there, and then we leave it on for another half and then go back up. So that will send us back across K-space this way, and we get an echo when you go through the middle. That's when the echo occurs, and then I won't draw that one in. So D, E, and so now we're at F. So now we're over at F here. And then you just sort of keep doing that. So if you look on the scanner, it says TE, time of echo. And so what does that mean? So like say it says like 32 millisecond echo. So, you know, what does that mean? You've got all these echoes. So what it means is the time to when you get through the center of K-space. So what will happen is the gradients will rapidly go back and forth like this. For a long time, like 32 times, until we've finally gotten up to the, so, you know, another blip occurs here, we go across here, another blip occurs there, go across here, etc. Eventually, we get through the, I'm not drawing as many as there are. Eventually we get up here and we actually go through the center of K-space. So when we do that, so that would be, so 32 of these in here. And then eventually we go through the center of K-space. And so what does that look like? So that would be, let's say this was the center of K-space. So what that's going to look like is a really big echo. So that will be, so you might wonder, well, how could this one be bigger than the earlier ones? Because don't we have like, you know, T2 star decay? So this echo will be described by this e to the minus t over t2 star. But these guys will be less. And the reason they're less is because, so those echoes, that initial echo like C, let me put the x-axis slightly above so we can see that's different than the x-axis. Kx. So the reason that these echoes are smaller is because the phase encode, this initial phase encode, has dephased everything, and so when you go through the center of Kx, the signal will be a little bit bigger, but overall that whole echo, so the center of it is when you go through Kx, but since you're really down in Ky, the total amount of signal coming out is much less because you dephased it. You scrambled up all the spins and wrapped them all up, and that's going to make a smaller signal. So by the time we finally get through here, this will be point FG. So this is point G. This is when we go through the center of K-space. So now we're back at the center of K-space, and that's the biggest echo. So so that big echo going through the center of K-space will be the one that defines what we call the quote-unquote TE. So the TE will be this time here. So however long it took us to get to the center of K-space. So that's TE. And then we do some more. So now, we've still got to collect 32 additional lines. So here's, 32 additional lines. In this little gap in time here, we went back and forth 32 more times because we just continued back up like this. And then finally, there's a little gap where we usually do another spoiler, and then we're ready to do another 90. So now here's the next 90. So this will be our TR. So TR, equals 1 to 2 seconds. TE is going to equal, say, about at 3T it's going to be something like about 30 milliseconds. Optimally it would be a little bit longer, but the problem is we want to collect lots of data, and so if we did sort of an optimal TE that was a little longer for the best T2 star contrast, it would take up more time. So usually people go a little short on the TE, 25, 30 milliseconds. So that's basically the echoplanar imaging. And so what you do is, what you're doing is you're just collecting all the data in an FID. So here's one FID, and all those echoes are occurring in that little FID. I mean, what it looks like, if you blow it up a little bit, what it looks like is you do the RF pulse, it starts to decay a little bit, and then you slam on the gradient, and then you put the gradient on the opposite way, and then the echo comes up, and then you slam it on the other way, and then the echo comes up again, and eventually you get to the center of K-space, and then the echo gets bigger at the center of K-space, and then it goes down. So it doesn't follow this envelope directly because you're messing around with the phasing code. And so until you get back to the exact center of K-space with Ky equals 0, the signal won't get big. So the signal will sort of start off big, then get big again, and then fall off more. So it won't follow this free induction decay because you've got the gradients on. And what makes the noise, so what does this sound like when you run it? It just sort of sounds like beep, 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 this really high-pitched beeping. And each beep is one slice. And so why is it that high? what you're hearing is this gradient going back and forth. So this gradient is going back and forth 1,000 times a second with, a 1.5 million watt amplifier driving it. And it's sitting inside a giant magnetic field. So it's basically just like a speaker. So they try to balance the torque, but basically when you power up the gradient coil, it's going to ever so slightly move. And then when you power it up the other way, it's going to try to move the other way. And so the gradient coil will sort of wiggle back and forth. And so that's actually what the noise coming out of the magnet is. It's the gradient coil ever so slightly wiggling back and forth as you run these 1,000,000 watt pulses through it. So that's echoplanar imaging. And the main advantage of it is that you can collect all the data for one K-space slice in like 60 milliseconds. So, and then you can go and quickly do another slice. So, typically you would do this interleaved, or, you do this. So while this, slice we just did is recovering, this is the next slice. Next slice. So slice select the next slice. Do the fat set again. Slice select the next slice, and then do the whole thing again for another slice. And so when you do this, so this isn't correct what I've written here. Sorry. This is not the next slice. This is repeat this slice. Repeat this slice. So you wait 1 to 2 seconds before you repeat this slice. But in the interim, the actual pulse sequence selects a different slice and does that one. And so this is the time to repeat the same slice. And so you can sort of record each slice every 1 second or 2 seconds. And so then and you need this, of course, if you're trying to sort of visualize the hemodynamic response function, because what happens is, why do we want T2 star decay, even though gradient echo is slightly more distorted? We want it because it gives us T2 star decay that detects static magnetic field offsets, which are caused by deoxyhemoglobin. And so as the oxygen comes in, it removes the thing that kills the signal and therefore makes the signal a little bigger. And so we need to visualize this over a short time course. And so that's why we're doing this. Now, one of the problems with echoplanar imaging, which we'll talk about next week, is it takes a long time. This is considered to be a long time to read out the data, because it might take like a full 50 milliseconds to read out this whole K-space. And there's a lot of time for distortions to occur. And the distortions come from B0 offsets that are not due to deoxyhemoglobin. So we can't do a T2 scan and get rid of the distortions due to static field offsets, because we're trying to record the static field offsets. So it's kind of sort of so the very same thing that cause the image to be distorted because of static field offsets are the very thing that we're trying to record, which is deoxyhemoglobin causing a static field offset. So so it's kind of like that's one of the problems. So you can't easily get rid of the distortions by doing a spin echo, because that would kill your signal, because you're actually trying to record the star part of T2. So that's echoplanar imaging. So what we're going to talk about now, and you can do a spin echo version of it. I'll talk about this a little later. I won't talk about it right here, but we could do a spin echo version. You might wonder, why would you want to do that? And we'll talk about why you might want to do that. So the spin echo version, you just add a 180 in there and set up the 180 so that this echo that you get is a spin echo. It's a gradient echo with a spin echo on top of it. And then you can also do a 3D version, which is called, echo volume imaging. And that basically just has, a bunch of phase encode steps in the partition, in the GZ. So that has various positive things and problems. So we'll talk about that next time. But what we're going to do now, so basically just to review, you got a fat sat, spoil the fat, do a 90 while you're doing the slice select, go to the lower left of K-space, and then rapidly go across. I forgot the blips, man, before I put the blips in here. So each time we cross 0, there's a blip. So every time we cross 0, we're going just up a tiny bit in the KY direction. So basically we go back and forth rapidly across K-space in the X direction, and then the blips slowly inch us up one line at a time. And then we collect all the data for one slice, and then while that one's recovering, do another slice, and then come back to this slice after 1 or 2 seconds. Okay, so now we're completely changing tack to talk about undersampling. And so one of the things that people figured out early on was, this was actually, back in the 90s, they started using coils, smaller coils that have higher signal to noise. And so what is one of the advantages of those? Well, intuitively, if you look at a smaller coil, so if you look at let's start with a big coil. So if you have a big coil, it has no spatial information in it at all, because it essentially receives signal equally from the whole brain. And so that was our initial, description of how the signal equation works. It's just picking up signal from the entire brain, and it doesn't have any spatial structure in it at all. So, but if you have a small coil, there's some spatial information in there. So here's the happy person in the magnet, smiling. Okay. They're carefully paying close attention. There's my alien in the magnet. Yeah, gotta work on my head drawing here. So now if we put a coil, like here, so here's the coil, there's the capacitor in the coil. So that's one coil, and we got another coil here. It's obvious that this coil is going to get a lot of signal from over here, and this coil is going to get a lot of signal from over here. And so intuitively, you can see there's some additional spatial information coming from the coil, because it's not like a big coil that picks up uniformly from the head. It picks up more strongly from one part than another. And you can actually use that information. But to understand it, we have to sort of consider, what does it do to K-space? And that's really the critical thing. So if we think about what something like that, a coil fall-off function, does to K-space, we can try to calculate we can try to use the convolution theorem again. See, it's a very useful thing, sort of for very useful conceptual thing, and the convolution theorem, remember, is if you convolve, if this is like one domain and this is another domain, so if that's the image domain and this is the spatial frequency domain, if we convolve in one, then we multiply in the other. And so we can sort of see what the effect of having a local coil is. And so let's start off with our brane and just say that our brane is a cosine. Now, I know that doesn't look much like a brane, but that's okay. But just it makes it easier. It actually sort of is like a cosine of cycle 1, but let's make it a cosine of, say, cycle. It's got some of that in there. So that's our brane. This is our brane. And so what we're trying to figure out is what happens when we multiply that by a coil fall-off function. So, so we multiply by our coil fall-off function. So say our coil fall-off function just happens to be a Gaussian. Not a very good Gaussian, but there it is. So this is our coil fall-off function. And so what does that look like? So when we do that, we get something that looks like, so I'll draw the envelope. So we get something that looks like a cosine, something like that. So it still looks like a cosine, but it's kind of falling off. Now, so this is our coil fall-off function, and this is the acquired image. So this is an image that's brighter in the middle. It's all image domain. So we're not in K-space, so this is all the image domain. Now, don't get this mixed up with adding, so, versus add. So if we added this, what would happen? We would end up with something that kind of looked like, let me do a better job of it. It would look like, it would run along this, so it would just be better job of it. It would be the same amplitude, but just, so here's our Gaussian. And say here's our amplitude. Yeah, so it would just be a cosine in there like that. So this is adding a Gaussian to a cosine. This guy is multiplying a Gaussian times a cosine. It's different. In the homework, there's examples of what happens when you add two different signals like this. So we're multiplying. So now, if we go over to the K-space, so if we do ft, so here's Fourier transform, goes back and forth. So what does that equal in K-space? Well, if it's just a cosine, it's just going to equal 2 spikes in positive and negative spatial frequency space, single frequency of our brane. So now, what happens if we Fourier transform a Gaussian? Well, we get another Gaussian, and it's going to be a narrow Gaussian because we started off with a wide one. Because remember, it's sort of Fourier transform is always the opposite. So if you start off with a wide Gaussian, we get a narrow one. If you start off with a narrow one, you get a wide one. So that's our, but since we're on this side, we have to convolve. And so so what happens when we convolve? So when we convolve, you can think of that, it's like Photoshop, like a Photoshop blur. So when you convolve, what you do is you take like an image, say a sharp image like this, and then you blur it with this function. You basically paste this function at each point along the way. If you paste the function here where it's 0, nothing happens, but as you get closer, as this function gets closer to the spike, it will cause a little blur in the spike. So what does that equal? So that equals basically some blurred spikes. So now what's going to happen is, like right where the spike was, instead of just a spike, you'll have a little blur. And then where this spike was, you have a blur there too. So what does that mean? So if we go back to the original description of the Fourier transform, we said that the Fourier transform was an orthogonal transform. And what that means is it decomposes the signal of, say, a brain image into different spatial frequencies, and those frequencies are orthogonal to each other, meaning they are uncorrelated from each other. So spatial frequency 2 is completely uncorrelated with spatial frequency 3, et cetera, et cetera. So if that's the case, if we were collecting k-space and we left some of the data out, we would be in trouble, because imagine we collected just every other line of k-space. So if we collected every other line of k-space, left this guy out, and then collected this line, left this guy out, collected this line, etc. So leave out. If we did that, what's going to happen, every other line. So that's good for us, because now we can get done in half the time. We've collected half as much data. It only takes half as long to do that, and so we can collect twice as many slices. But if we have an orthogonal decomposition of k-space, we just left out half the data, and that data is all completely uncorrelated. So, the data in this left out line can't be predicted from the surrounding lines because it's completely uncorrelated, because that's the definition of the Fourier transform. But now look what's happened over here. What's happened over here when we use a coil that has a local field of view, what it does is it takes spatial frequencies in our image, the spike-like spatial frequencies in our image, and it kind of moves them off to the side a little bit. It smears them out. Smear. I call that's a technical term. It's smears spatial frequencies. Now, it's important to not think of this as smearing the image. So when we take the inverse Fourier transform of this, we get a sharp image. It doesn't blur the, when you do this operation by doing multiplying by a coil fall-off function in the image domain, causing some spatial frequencies to kind of smear outward to nearby spatial frequencies, that smear doesn't then cause a blur in the image when you inverse Fourier transform it. You just get an image that has a bright spot. So the Fourier transform of this thing is basically the same cosine, same sharp cosine, doesn't change the frequency of the cosine, but it's got this sort of fall off. It's got a bright spot in the cosine. Now, in the last minute, the most critical thing about this, is that the same argument applies to any frequency. So that's the most critical thing. So star, 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 star. So same argument applies to all spatial frequencies. That's the most critical thing. So it would be nice to sort of visualize it more like getting spatial information out of the local coils, but the way it actually works out is it's a little counterintuitive. So as a result of having a local field, local pickup in the image domain, we kind of blur our spatial frequencies into adjacent lines of K-space, basically. And so what that means is that there is some information in these surrounding data points that can be used to fill in the data. So how does that work? So basically how that works is we have to sort of figure out, and because the same argument applies to all spatial frequencies, we can do the following. So we can collect all the data in the center of K-space, where the signal is big, and then when we're away from the center of K-space, skip lines on our first scan. So what is that for? So because the same argument applies to all spatial frequencies, what we can do is we can take a point here and then figure out, by using the surrounding points, to predict it. So basically you can interpolate the K-space by taking completely sampled, so fully sampled K-space, and then we basically make what's called, a GRAPPA kernel. And what's the GRAPPA kernel? The GRAPPA kernel is just, given these data points, we try to predict this point. We actually recorded it, so that's how we can sort of optimize our prediction, because here we've actually recorded that point, and then we just try to figure out, like, given these points, what is that one most likely to be equal to? Once we've done that, that thing applies across all spatial frequencies. So then what we can do is, once we have that, we can just leave out half the data points and then use the GRAPPA kernel to fill them in. So then we just record that one, leave that guy out, record that one, leave that guy out. And so now we can go twice as fast. Now the only way this works, it's a critical point, the only way this works is because of the smearing business. And the smearing business in K-space, smearing business in spatial frequency, means that there is some information in the surrounding lines that we can use to reconstruct the data that we left out. And that's what causes GRAPPA to work. So GRAPPA is this method of interpolating K-space, but it's also what causes, another version of that called sense, or just, general linear inverse that I talked about in one of the graduate sessions. So the general linear inverse wouldn't work if we left out some of the data and then tried to do the inverse reconstruction, unless this had occurred. So the only reason it works is, the only reason that the general linear inverse works, the only reason that GRAPPA works is because of the fall off, the K-space data has been sort of smeared out. And so then that means that there's some information left when we leave out a line. So I didn't understand this for many years. I sort of understood somehow you're going to be able to get spatial information out of the fact that you've got these coils picking up different parts of the brain. But this is the very counterintuitive way that it works. So as a result of the coil fall off multiplying our signal, it smears the data out in spatial frequency, then that allows us to reconstruct this data that would normally be completely orthogonal, completely uncorrelated, and it's no longer uncorrelated. You can actually predict the missing data from the surrounding samples. Okay, so that's quite a head full. We'll stop the recording here, David, and take some questions.